Hey everybody, I'm a little worried that the examples we did of correlation may have given you the wrong impression about something. If you look at the first example where we had a positive linear correlation, the whole reason there was a linear correlation was that the number of cousins clearly determined the number of birthday parties. Having more cousins would cause you to have more birthday parties to go to. If you look at the second example where we had a negative correlation, negative linear correlation, the whole reason there was a linear correlation is that, for this person anyway, the protein intake clearly affected the carbohydrate intake. Changing their protein intake caused a change in their carb intake. And in the third example, where we had a nonlinear correlation, again, the reason there was a correlation is that the area of the square was determined by the side length of the square. If you make the side length of a square longer, that's going to cause there to be a larger area. So what I'm worried about is that these examples will give you the impression that if there's a correlation between two variables, then one of the variables is causing a change in the other variable. And that's just not the case. This can be summed up with the phrase, correlation is not causation. Just because two variables are correlated does not mean that one variable causes a change in the other variable. For example, there might be a confounding or lurking variable that's causing both changes. And we saw an example of that back in section 5.1. But it could also be that the correlation is pure coincidence. And I've got some examples for you of that. If you look at all three of these scatter plots, there's a really nice linear correlation between the x and the y in all of them. You can draw a nice straight line through the dots. All three of these have a very tight, positive, linear correlation. But let's look closer at what the x and y variables in each of these are. In the first one, on the horizontal axis, so the x variable, we have the number of registered nurses in Arizona. On the vertical axis, so the dependent variable, we have the distance between Saturn and Earth. Now, if a bunch of registered nurses move to Arizona, so there's more registered nurses in Arizona, is that going to cause Saturn and Earth to be further apart? Of course not. That's ridiculous. If you look at the second one, on the horizontal axis, we have the average length of Smarter Every Day, so that's some YouTube channel, the average length of their YouTube videos. The vertical axis is the popularity of the first name Nico. So if the person who runs Smarter Every Day starts making longer YouTube videos, does that mean that the first name Nico is going to become more popular? No, again, that's completely ridiculous. And the last one, The average number of comments on Mr. Beast's YouTube videos is the horizontal axis. And the dependent variable on the vertical axis is the number of social and community service managers in Alaska. So does that mean that if Mr. Beast YouTube videos get more comments, suddenly there's going to be more social and community service managers in Alaska? Again, that's completely ridiculous. In fact, these are so ridiculous, you might think the numbers are made up. But you know what? They're not. I got these all from the website of a guy named Tyler Vegan, who has a whole website devoted to coming up with these. And he explains on there what he does. He will, for example, get a bunch of data on, say, the number of registered nurses in Arizona. And then he'll get all kinds of data on all kinds of other things, and he'll just start going through the data to see if there's any two that match up. Well, in this case, nurses in Arizona matched up to the distance between Saturn and the Earth, even though they have nothing to do with each other. Of course, Tyler Vegan is doing this on purpose, coming up with correlations that are so ridiculous they're actually funny. But he's making the point that just because there's a correlation, you can't assume there's causation. And the reason it's important to make that point in as memorable a way as possible is that it's not always so obvious, especially if it's plausible that one thing causes another thing. It's so easy to see the correlation and think, oh, hey, that proves that the one thing caused the other. So just to recap here, two variables are correlated if there's a mathematical relationship between them, but this does not mean there's any sort of causal relationship between them. Causal just meaning that one caused the other.